We continue with graphics, but not in the format of graphical algebras, and Paul is giving the talk. It's John. John, go ahead.
Thanks for the introduction, Bart. Okay. So this is based on joint work with my co-authors, Robert Booth and Titouan Carette. So I'm currently in France at Nancy, and Robert is in Edinburgh, and Titouan is in Paris. And we submitted 2 different talks this conference, and I thought that maybe one of them would come and present one of them, but it's only me. So I'm presenting 2 talks in a row. So I've like unceremoniously given myself like a distinguished talk by combining them together. So I apologize to the organizers. But yeah, both of the papers are by the same co-authors. Okay, yeah. So this is like the first half is going to be necessary to understand the second half. So hopefully no one shows up late. Okay, so I can't speak for my co-authors, but my motivation behind this is that I'm not good at math, and maybe it's the same reason why pictures are so nice to teach quantum mechanics to high schoolers, because when I was in high school and I saw all of these equations, I was just completely confused and I didn't understand anything. So my motivation is to like take these complicated mathematical things and then turn them into pictures so that I can understand what's actually going on. So Bob probably already talked about this in the last talk, but I'm going to be using a lot of string diagrams. And the first kind of class of category that I'm going to be interested in is a prop. So formally, this is a strict symmetric nodal category generated by a single object under the tensor product. So you have like these boxes, which are your morphisms, and wires coming out and leaving them. And the number of wires is like denotes the number of inputs, and then up. So if there was like 3 wires here and 2 wires there, then that's a thing from 3 to 2. And if you glue the wires together, then this is the composition. And if you paste the diagrams atop each other, that's the tensor product. And you can kind of exchange wires and pass them through with naturality. And in some special cases, you can actually bend wires around, which gives you a lot more flexibility. And that's called compact prop or compact closed prop. So the first thing which I want to understand from a graphical point of view is linear algebra. So this is kind of a review. So when people talk about linear algebra, I think a lot of times actually they're talking about affine algebra. So if you have some field, then affine transformations between finite dimensional vector spaces can be represented by their homogeneous coordinate matrices. So if you have like an affine transformation with a linear part T and an affine part A, and then similarly another one with a linear part S and affine part B, then you can kind of put them in this augmented matrix where you always have a 0 here and a 1 here. And when you do matrix multiplication, this corresponds to the composition of affine transformations. So, I mean, to me, this is kind of confusing. I don't know about you guys, but to turn these into pictures, you can generate all of the affine transformations between finite dimensional vector spaces with these generators. So the first one is like your copy map. And this is just a vector, 1, 1, with no affine part. And if you feed in a scalar here, then it like copies them onto both of the ones. And this is the addition, which is just the transpose. If you feed in like a vector A, B, then it sums them together. And also you have these, you can have, some of the dimensions can be 0, which is why I've drawn stars. So then the discard morphism takes in nothing and just produces 0. It takes in anything and produces, takes in nothing and produces anything. And then this takes in anything and produces nothing, and this takes in nothing and produces anything. And then this guy is just the affine shift. So it takes in nothing and produces 1. And for every element of the field, you have scalar multiplication. So it takes in some B and then multiplies it by A. And this is a well-known thing. I don't know who actually proved this originally, but you can capture all of the rules of linear algebra or of affine transformations in terms of these equations. So the copying forms a co-commutative comonoid. The addition is a commutative monoid. No, the copying is co-commutative monoid. The addition is a commutative monoid. And then together they interact to form a bialgebra. And then there's also rules involving the scalars. Like if you have two scalars and you connect them together, this is just multiplying them. And in particular, the zero scalar is the unit for the Hopf algebra. So it's like discards everything and produces zero uniform constantly. And then scalar one is just a wire. And if you have two scalars and you take the convolution under the bialgebra, and this adds them. And then finally, you have these rules for the affine stuff. So if you have just a constant affine shift by one, this can be copied and deleted. So already, just using these simple pictures, you can capture all of affine transformations, at least between finite dimensional vector spaces. So here's an example. I've just like kind of arbitrarily made some string diagram here. And then I've simplified it to a normal form, which you can always do, which is kind of a form. This is like doing matrix multiplication. But the way to interpret this is you put like variables on the input wires and you chase them through the diagram. So like if this is x0, you chase it through, and when it meets the b, you multiply. X1 meets the b, multiplies. They sum together here, and this sums with x2 to get x0 plus times b plus x1 times b plus x2, and so on. So that what you're doing essentially is just computing the matrix. So if these are your like indeterminate variables, when you multiply them by this matrix, then you get the stuff on the right. So this is how you'll do this translation between the string diagrams and the matrices. And of course, you can go the other direction because this is an isomorphism. Okay. So this is, I'm kind of hiding some technicalities under the rug, but something that I'll be using is the fact that if you have a prop, you can strictify it, even though it's already strict. You take the symmetric monoidal strictification of this thing to get you a prop now with more morphisms. So I'm going to draw like thick wires to represent the fact that you have a bunch of wires bundled together. So if I draw like an N on top of this thick wire, this means that there's like N individual wires. So this is like, and then you have these generators which like combine the wires and bundle them into a thicker wire. So N wires and M wires, bundle them up, you get an N plus M dimensional wire, and you can unbundle them by doing the opposite. And these two things are inverse to each other. So if you do this, then you can kind of avoid having ellipses in your diagrams, and you can, by induction, define things like block matrices. So I didn't include the base case, but you can just, if you can now, before was a scalar, you've taken it, you can have like this block matrix, and you can decompose it into copying inputs, multiplying them by the submatrices and adding them together. Where a single wire, if you just had a single wire, this is just the original scalar. And then for the affine shifts, if you just combine them into a wire, this is like shifting now by a vector. Yes, and in some sense, I feel like when people are doing linear algebra, they're not actually just working with matrices, they're working with subspaces. And then the correct categorical semantics for subspaces is relations, in my opinion, at least. So there's a series of papers on linear relations and affine relations by Bonnke and co-authors. And the idea is that you take the category of relations internal to affine transformations. So here, the objects are again just natural numbers, but now the morphisms are affine subspaces between the direct sum of the vector space with the input dimension n and output dimension m. And the composition is just the same as the relational composition of sets. But in particular, if you take the relational composition of affine subspaces, you get back again an affine subspace, provided that you allow the empty set to be an affine subspace. And the symmetrical model structure is given by the direct sum, and also the compact structure is the same as the compact structure of relations. And again, you can give generators, and I've done them in kind of spiders, which is reminiscent of the ZX calculus, which Bob talked about in his talk. So this gray spider, what it does is it relates vectors together only when they have all of the same elements. So you have, for all A in your field, you have these two vectors, then they're related. And if anything is different, it's not related. So it's like, it's the empty set. And then you have this white spider does the same, but for addition. So what it does is it sums the input vector and sums the output vector together and asks that it's equal to A. So A is the affine shift, and this is an affine equation, not a linear equation, coming from this A. And again, you have the same scalar multiplication, which takes an element of the field and then just multiplies it by this label A. Yeah, so in Bonke and All's paper, they give relations for this, and I've slightly changed them to make them look more ZX-like using spiders. So the first equation that you impose is that these two spiders are commutative, so it doesn't matter which order the inputs and outputs are connected to the spider, it's the same. And it's also undirected, so in a sense, if you had one of the inputs wrapping around here, then it's the same as just adding an extra output. And you have these equations that make them into Frobenius algebras, essentially. And so on. And you have this kind of similar equations to affine transformations. But what I've secretly done in order to make both of the spiders undirected is I've taken the embedding from affine matrices into affine relations, the graph, which sends an affine transformation to this relation here. And in terms of the generators, I've had to insert an antipode so that I can keep everything directed and not have to worry about the orientation of the edges. So just as a little bit of a warning. Okay, so that's the kind of basic language which I will build everything up from. And I'll try to use this to talk about classical mechanics and the mathematics of classical mechanics, which is symplectic geometry, at least the linear form of it. So I'm going to take this example of electrical circuits because in their paper, Brendan Fong and John Baez use this example, and they had a quite nice exposition. So perhaps people will be familiar with this. So if you have an electrical circuit, you can characterize the extensional behavior of the circuit by how it transforms the current and the voltage. And there's these two important laws due to Ohm and Kirchhoff that if you have a node in your electrical circuit, which is open, then the voltage around the node is equal to the current multiplied by the resistance. And the sum of currents flowing into the node is equal to the sum of currents flowing out of the node. So for the example of a resistor, a linear resistor, so we're assuming that it behaves really nicely mathematically, which in practice is not so true. It has resistance R, which is a positive real number. And the incoming voltage and current is Z0 and X0. And outgoing current and voltage is Z1 and X1. By Kirchhoff's current law, the currents equalize, so the ingoing and outgoing current is the same. And by Ohm's law, the outgoing current is the ingoing current plus the incoming resistance or incoming voltage times the resistance. So this is actually an affine transformation, but affine transformations are not general enough for our purposes. So I'm going to consider this as an affine relation, and I'm going to use these string diagrams by Bonke and All, which I just exposed. And the idea is now that a single electrical circuit wire you decompose into two parts. And the first part is like the subspace for the current, and the second part is the subspace for the voltage. So using these string diagrams for affine relations, which I just described, you have your resistor here with one wire coming in and one wire going out, which is this two-dimensional wire here, and you pull it apart and you copy the current, multiply by R and add that to the resistance. And then if you bundle this all up, you should think of this as a and yeah, so the reason why I want to use affine relations and not just affine transformations is because there's lots of components which are not actually functions. They're just subspaces. For example, this thing which was also in Bayes and Fong's paper, which is you have a ideal junction of wires that are all connected together. So imagine wires and you just literally solder them together by these two laws which I described. The current up here is summed. So this is the summing spider, and the voltage is equalized. So this is a relation. And then you have another affine function, which is the voltage source. So what it does is it does nothing to the current, and the voltage, it just sums the constant voltage V, which is there. But from my point of view, this is kind of a bit ad hoc, and I don't really know what's going on. Like this is just given a bunch of examples, but there's not really any structural picture. And the idea is that this is an instance of a more general phenomenon. So in classical mechanics, not just in electrical circuits, the behavior of systems is characterized by their interaction with position and momentum. So I've taken this table from Bayes and Fong's paper, as well as this guy's thesis, Smith, and I've given a bunch of examples. So you have translation mechanics, electrical mechanics, hydraulic mechanics, and thermomechanics. So in the more general picture, you have the translational picture. The position is just position, and the momentum is just momentum. Whereas in electrical circuits, the position is charge, and the momentum is voltage. And sometimes people refer to their time derivative instead of the actual quantity itself. But also, if this helps your intuition, in hydraulic mechanics, the position is volume and the momentum is pressure. So you can think of, like, for instance, this wire junction as just like some idealized junction of pipes that are all connected together. And you can also think of thermal mechanics, where you have entropy and temperature. So this thing that I did with, you have a wire and you decompose it into two parts. This is called the phase space. So if you have like n particles in your classical mechanical system, you can always decompose it into a vector space of dimension 2n. And the first grading, which I've like given the subscript z, is the position, the general position grading, and the x is the general momentum grading. And together that's called the phase space. But that's kind of cheating a bit because the phase space has a bit of extra structure. So if you have two configurations of phase space, they're called compatible when this equation holds. So you take the position of the first particle, and you take the inner product with the momentum of the second particle, and you subtract that from the position, from the momentum of the first particle, inner producted with the position of the second particle. And they're compatible when these two things are equal to each other. And this kind of equation is captured by this bilinear map, omega, which is called the symplectic form. And together, this vector space with this map is a symplectic vector space. And these subspaces, which I've described, like the junction of wires in the resistor and the voltage source, this is an affine Lagrangian subspace. So the idea is that this is like a maximally compatible configuration of phase space. But yeah, so this was all exposed in Brennan and Fong's paper and Bayes and co-authors' paper a few years later. So here's maybe that was a bit unclear, but I want to give some more intuition. And for this talk and the next talk, I'll give the example where n is equal to 1. So you just have a single particle because it's easiest to visualize. In higher dimensions, I don't know how to visualize like a 4-dimensional linear subspace. So you have this vector space of dimension 2 and this symplectic form omega 1. And what it does in affine space is it captures the area of parallelograms. So if you have these 2 points, one which is like a particle with the momentum p and position q, and the other with momentum x and position z, then the symplectic form of these two things is the volume. And compatible points are collinear. So if you have a subspace where everything is compatible, then this just means that you have a line in phase space, which means that it has no volume. And the idea is that these subspaces don't correspond to single particles, but like an ensemble of particles flowing together in a compatible way through phase space. So if you have an ensemble of particle with constant momentum, then the position may change, but you can kind of think of it as things are all flowing together in a way nicely together that is compatible. And yes, you can also compose these things as affine relations, and this compatibility is preserved. So there's these two papers where they expose this. Gimin and Sternberg published it first, but in their paper they give attribution to Weinstein as where he did this in his lecture, I think, and didn't publish it until later. So it's still a prop, but now the morphisms are these affine Lagrangian subspaces of the product. So the subspaces all have even dimension, and the composition is still relational, and the tensor product is still the direct sum, and also you still have the compact structure. And for the more physically inclined, like I know Owen on Tuesday, I think, gave this talk about wheeling machines and mechanics and stuff. There's this embedding from affine relations into affine Lagrangian relations, which doubles things. And it sends a subspace here to the orthogonal complement on the momentum part, and on the position part, it just takes the original subspace. And this comes from the embedding the vector space into its cotangent bundle. But because everything here is linear, we don't have to talk about manifolds and cotangent bundles. It's just vector spaces, right? Because, for example, the cotangent bundle of a vector space is just isomorphic to the vector space dual, a direct sum with a vector space. So you get this even dimensional thing. So a few years ago, Alex and I, we gave generators for this prop, but no equations. And we showed that for any field K, it's generated by these two types of spiders, which kind of generalize the affine relations picture. And the spiders are decorated by, each of them decorated by two elements of the field. So for the gray spider, I'll draw it like this, and it like expands into affine relations as summing the positions and adding and asking that the momentums are the same, and then it takes the momentum and multiplies it by b, and adds that to the position. And then the other kind of spiders does the same thing, but in the opposite direction. And together this generates this whole category. And then in the current paper, which I wrote with Robert and Titouan, we actually completed the picture and gave equations. So again, we asked that these spiders are commutative and undirected so that the order doesn't matter. And then we impose several equations so that, like, when two spiders of the same color are connected, they fuse together and then the phases sum. And again, for the white one, we introduce an antipode so that we can retain this property of being commutative and undirected. And then we have a bunch of equations, which I'll get back to in a bit. And also importantly, we have the Fourier transform. So this box here with no label, what this does is it changes the colors of the two spiders, and this corresponds to the symplectic Fourier transform. Yeah, and this embedding, which I talked about, which is induced by the cotangent bundle, the embedding into the cotangent bundle, what it does is it takes your affine relation spider for copying, and it just gives it sends it to the gray spider with no phase. And it takes the one for addition, labeled by the affine shift A, and it inserts the affine shift in the first component and does nothing to the second. And then for scalar multiplication, it just sends it to scalar multiplication. And what's really nice is examples of electrical circuits, which I gave. Since everything is already pre-bundled together, all of the wires secretly correspond to two-dimensional vector space. I don't have to do this thing, which I decompose things So a junction of wires connected together is just now a gray spider, and a resistor is a white spider labeled by R, but had to introduce this antipode for bookkeeping purposes. And then a voltage source is pretty much the same thing, but now the voltage, which is being constantly added, is now put on the left instead of on the right. Yes, and so in their paper, Bonke and all, where they talk about affine relations, they give like ways to rewrite electrical circuits, but they do this in this doubled picture where they always have to carry around 2 wires for every corresponding to every electrical circuit wire. But here we don't have to do this. Everything is already kind of bundled together and combined, which allows us to give really clean rewriting proofs of circuits. So for example, imagine you have 2 resistors, both with resistances R0 and R1, with their positive real numbers. What you do is you take your electrical circuit wire and then you just solder it to 2 other wires. So it splits in 2, and then you compose the resistors in parallel, and then you recombine the wires. And you can do this series of rewriting coming from our equations. You unfuse the resistances, you apply the bialgebra law. No, this is just you just kind of rearrange things so it looks like the bialgebra law, and then you apply the bialgebra law, and then you apply this rule which allows you to change the color of these things which are carrying resistances, fuse them together, apply this rule in reverse, and then now you get this guy over here. So the idea is that if you compose 2 resistors in parallel, then extensionally, in terms of its position and momentum, or current and voltage rather, this behaves like a resistor with this resistance. And the idea is you can kind of think of this non-deterministically, where you have, in a wire, you have like a bunch of resistors kind of like flowing through your wire, and then they non-deterministically branch at these junctions where they're impeded by the resistors, and then they merge back together, and then in the end somehow this corresponds to something that behaves like a resistor with this resistance.
So you come to a conclusion. Yeah, well, you're stealing away time.
Oh, yeah. Yeah, so this color swap rule, it's like you can describe this state in terms of a function of position like this, where the intersection is on this line, or you can describe the same line as a function of momentum. So that's where this is coming from. It's like a change of reference frame. And we can define, by taking this strictification, we can define higher dimensional spiders, so that by induction, now they're labeled by a vector, which is like an affine shift, and then a symmetric matrix, which is like a graph. And then we give more identities so that you can just directly represent these things and reason about them without ever having to decompose them into smaller systems on higher dimensions. So the advantage of this is that if you have like a network of resistors and voltage sources, you can represent the extensional behavior in terms of a positive definite matrix called the impedance matrix, and an affine shift, which gives you the voltage. So that if you look at the jth wire and the kth wire, then the resistance between those 2 wires is given by this element of the matrix. And because it's symmetric, it doesn't matter which way it's going. And the cool thing about this is that just as you can compose resistors in parallel, you can now compose, say, for example, networks of resistors in parallel, where you don't necessarily know the internal structure of the thing, you just know the extensional behavior and how this changes the current and the voltage. So imagine you have such a system R0 and a system R1, where maybe inside there's a bunch of resistors wired together in some configuration, but you only know with like a multimeter how the resistance changes. You can just do the same proof, but where everything is thickened, and you now have you now know the extensional behavior of the system where they're composed in parallel. And that's the end of the first talk.
The last slide, what's the one over a matrix?
Oh yeah, because you need to assume that they're positive semi-definite. look, strictly positive definite, then you can invert the matrix.
That's the element part.
No, the literally the inverse of a matrix. Yeah.
Further questions?
Alexa.
Would there be a way of replacing these, one over the sum, having this as a string diagram as well, with
In a sense, because you just change the color and then that's the inverse. So here you have your R, and then the inverse is just when you change the color up to an antipode. Yeah.
Further questions? Think you can go through the response.
Okay.
Right.